My name is Gabriel Tarasuk-Levin. I've been a vMotion engineer for the last 4 years or so, and I'd like to get you started with insight into vMotion, architecture, performance, best practices, and a look at our roadmap. First of all, just standard boilerplate warning. We will be talking about future technology here, all of which is definitely subject to change. And also, we'd like to take questions at the end of the presentation, so please hold questions till then. Everyone here knows that virtualization has really penetrated data centers across the world. And along with virtualization has come vMotion. vMotion is one of our most popular features in vSphere. It's deployed in something like 80% of vSphere production environments. Estimates suggest that there's something like 5.5 vMotions issued every second, which is more than the number of planes taking off globally per second. And storage vMotion is similarly popular. It's deployed in something like 70% of enterprise vSphere environments. So very popular features. Between vMotion and storage vMotion, we've given administrators a lot of flexibility in the way they manage the interaction of their virtual and physical resources. But even with those tools, there are still some physical and management boundaries that we're not really addressing today. We think we can do a lot better. Let me start walking you through our story. In order to understand where we're going, it's important to understand where we are today. So first of all, let's just start with talking through vMotion a little bit. I imagine everyone here is pretty familiar with vMotion. It's our feature that lets you move a running VM between two physical ESX hosts. The migration is entirely transparent to the running VM. It doesn't know that it's been moved. It's just running happily the entire time on the physical ESX host. We send the VM's memory disk, or memory virtual device and CPU state over the vMotion network. vMotion today does require shared storage. And vMotion is a key foundational feature in vSphere. It's used by a whole bunch of higher level features. For example, DRS, our distributed resource scheduler, uses vMotion to move around VMs to balance load in your cluster. DPM uses vMotion in order to evacuate hosts and power off hosts to save you power. And we have FT. FT actually uses vMotion to create secondary copies of VMs in order to start the fault tolerance process. While there's a lot of detail around how vMotion works, it's really important to understand one of the core challenges of vMotion, how we move your VM's memory state. Because we're potentially moving, terabyte VMs over the vMotion network transparently without interruption to the VM service. So how does that work? We use a technique called iterative precopy. The idea here is rather intuitive, I think. We step across your VM's memory state, making a copy of all the VM's memory. As we do, we watch to see what memory pages the VM is dirtying. Then we go back, once we finish the full copy, and just send the delta. So we send whatever changed while we're making the first copy. While we're sending the delta, we watch to see what memory content the VM changes. Then we make another pass and send that delta. So the idea being, we're making passes across your VM's memory state and always sending deltas relative to the last iteration of precopy. The idea here being, provided the deltas are going smaller each iteration, we'll eventually converge down to few, if any, remaining pages to transmit over the network. So this way, we can send your memory state while it's changing over the network. So let's take a look at an example of this, given a 40 gig VM. We start by walking across its memory state, sending all 40 gigabytes of memory to the destination host over the network. As we do, it's still running, so let's say it dirties 20 gigabytes of memory. So we have to go back and send that 20 gigabytes of memory over the vMotion network. As we do, because it's still running, let's say it dirties 11 gigabytes of memory. So we go back and send that. As we do, because it's still running, it dirties 5 gigabytes, so we have to go back and send that. For the purposes of this slide, let's say we're done now. But in reality, we would have kept going until we converged down to a few outstanding pages. And then we would have proceeded with the switch over. So it's one of the core technologies behind vMotion. Now let's switch over quickly to talking about storage vMotion. Again, I imagine everyone here is pretty familiar with storage vMotion. It's our feature that lets you move a running VM's storage between two different data stores. So you can power on a VM on one host, decide you have to move its storage, and transparently move the underlying VM DKs off of one data store connected to the host to another data store connected to the same host. The VM has no idea its storage is being moved underneath it. While you're doing the storage vMotion, we will move your VM snapshots, and you're welcome to transform your disk type as well. If you have thick disks, you can convert them to thin disks or thin to thick. And like vMotion, storage vMotion is a foundational feature. It's used by storage DRS to rebalance your VMDKs across your data stores for load and space purposes. So again, let's take a look at how storage vMotion works. Clearly, the most interesting detail there is how we move your VM's disk content. So instead of some sort of iterative approach like precopy, which we have done historically, but nowadays we use something a little bit more tuned to disk traffic, we use something called mirrored mode storage vMotion. Again, I think the idea is pretty intuitive. We want to make a linear clone pass of your disk. As we do that, though, we just watch what I/O the VM is issuing. And if we see the VM try to write to a region we've already copied to the destination data store, we just split that I/O and mirror it to the destination data store. So as we're doing that, we're making this linear clone pass, we're keeping the disks in exact lockstep. So we never have any sort of delta. The destination is never behind the source. It's always synchronous. So at any given time during this mirrored mode storage vMotion, there are 3 different types of disk regions. The first is the disk region we've already copied, meaning that because we've already copied it in the linear clone pass, whenever the VM tries to write to that region, we have to split the I/O, mirror it to the destination data store before we ack it back to the guest. There's the region we're currently copying. This is just a 64 meg region. For the duration of that 64 meg copy, we prevent guest writes to that region. We just defer the I/O. That's just to avoid races between copy I/O and guest I/O. Finally, there's the region we have not yet copied in our linear clone pass. And the VM is free to write to that region. The linear clone pass will catch up to it eventually, and then we'll just copy the content then. So let's take a look at an example of how this plays out. Let's take a run of VM. This is just an illustration of VM's disk. It starts out as being entirely not copied yet. So the VM is free to write anywhere in that region. We start by locking a 64 meg region to copy. We copy that region to the destination disk. And then we want to progress on to the next 64 meg region. So we lock the next region and copy that. So now we have an example of 2 regions we've copied and a whole bunch of regions we haven't yet copied. So that means if the VM tries to write to a region we've already copied, we have to split that I/O and mirror it. So let's take a look at an example of that. So as you saw, the VM tried to write to a region we've already copied. We mirrored that. In parallel, we continued the copy process. So let's just proceed along with the linear copy. We make 64 meg copies and mirror I/O to regions we've already copied. The linear pass proceeds along, mirroring I/O along the way. And eventually, the linear copy is complete. At this point, any I/O, any write I/O to any region of disk has to be mirrored to the destination data store. But because these disks are now in lockstep, at any time we can switch over to using the destination disk as our primary disk. Basically, we're done with the source disk now. So that's the core technology behind storage vMotion. Given those core features, now we can talk about something we've announced here for the first time, unified vMotion. Steve mentioned this in his keynote on Monday. He described it as our new enhanced vMotion. Unified vMotion is our feature that lets you atomically move a VM's memory and disk state together over the vMotion network. Another way to think about this is vMotion with the requirement of shared storage. So, for example, if you want, you can power on a VM on a host with only host local storage, and use unified vMotion to move that VM, its memory state and disk state together atomically to another host, potentially another host's local storage. All this data is sent over the vMotion network. There is absolutely no requirement of shared storage here. And again, this is still entirely transparent to the running VM. Maintains the same properties as the vMotion and storage vMotion. So let's take a look at how this works. We already talked through the storage vMotion architecture, so this slide should look very similar. That's because we leverage the same architecture. This is, in fact, the storage vMotion architecture just enhanced to work over the network as well. So you'll observe we still have the same linear copy pass. We're still doing I/O mirroring. The primary difference is that the source host can't write directly to the destination data store because it could be over some remote network or partition or the like. So instead, we have to send the data over the vMotion network. So as we're doing this linear clone pass and I/O mirroring, we have to put any destination side I/Os in a transmit buffer. That buffer is drained over the vMotion network. It uses the vMotion protocol that we have developed over the years. That's drained at the destination host into the destination data store. Otherwise, this is the same linear clone pass with I/O mirroring just over the vMotion network now. Similarly, let's take a look at vMotion, or the memory copy approach of vMotion. Unified vMotion leverages the exact same technique. As we go, we are doing iterative precopy passes of your VM's memory state. At the same time, though, because of the way we do the disk copy and the memory copy, it's possible that at the same time you could have mirror I/O going over your vMotion network at the same time as your vMotion's memory state. So we'll take a look in the performance section later about how these two interact. Now, I mentioned in vMotion that we're doing iterative precopies. It's important to keep in mind that, as I described, iterative precopy only works provided that the deltas are getting smaller every time. I mean, the whole point is every time you're saying smaller and smaller deltas. In ESX 5.0, we developed a feature called SDPS, or stun during page send. The idea being, if we observe that the deltas aren't getting smaller, that is, your VM's memory is changing more quickly than we can transmit it over the vMotion network, we have to take corrective action. So SDPS, as I said, introduced in 5.0, injects microsecond delays into your vCPU's execution of your VM's workload. The idea being, during vMotion, if need be, if we're not managing to transmit your VM's memory state, we'll disrupt the VM's workload just enough to allow precopy to converge. I mention this now because unified vMotion leverages the same vMotion precopy architecture, which means it also gets to inherit the benefits we invented over the years, such as SDPS and multi-NIC. So all of those features still apply to unified vMotion. And we'll get back to that a little bit later, too, in the performance section. So let's put this all together. First of all, in a unified vMotion, the first step is we copy your disks. This is still, as I mentioned, the mirrored mode storage vMotion, so it's the linear clone pass with I/O mirroring. Once we've successfully cloned all of your disks, while the mirror I/O is still going on, we start the memory precopy. So that's the iterative precopy. If needed, we enable SDPS to allow memory precopy to converge. Once memory precopy converges, then we quiesce the source VM, transfer the VM's virtual device and CPU device state to the destination host, deserialize that state, and resume the destination VM. Once the destination VM has resumed, we can tear down the source side state. And then your unified vMotion is done. The destination VM is now your primary execution context. So at this point, I'd like to hand off to my colleague Min Kai, who will talk through unified vMotion's performance.
Thanks, Gabe. So now that we have talked about the architecture of vMotion, story vMotion, and traditional vMotion, you must be curious how the performance of unified vMotion, how does it compare to our traditional vMotion and story vMotion? To answer those questions, we first have to know how to measure the performance of unified vMotion. In this performance study, actually, we defined 3 different metrics. The first metric is the migration time, which can be broken down into 3 components. The first component is the time to migrate the disk state of the VM. The second part is the time to migrate the memory state of the VM, and as well as the total time to migrate the whole VM. The second metric is the switch over time, which measures the time for us to switch the VM from source ESX to destination ESX. So this time should typically be less than 1 second. The third metric is the guest penalty, which measures the impact to the guest workload during the VM migration. For all those 3 metrics, we want to minimize them so that we can have best performance. Now, how do we measure those metrics? For the first migration time and the switch over time, we have our profile tools, which are going to extract the timing information in source and destination VM kernel logs, as well as the VMX logs. To measure the guest penalty, though, we actually configured the benchmark tools in the guest so that we can measure the guest workload. For example, if we have database workload running in the guest, then we're going to measure the guest performance in terms of like number of orders per second. So in this performance study, because as Gabe talked about before, we have the disk migration and the memory migration. We want to study them separately. So the first experiment we did is to compare the disk migration performance between unified vMotion and storage vMotion. In this experiment, we actually run disk I/O intensive workload in the guest so that we can stretch the disk linear clone path. The second experiment we did is to compare the memory migration performance between unified vMotion and traditional vMotion. In this experiment, we run some CPU and memory intensive workload so that we can exercise the memory precopy code path. Actually, we even inject the workload large enough so that the simple memory precopy wouldn't converge. The third experiment is that we're going to measure the unified vMotion performance over metro distance. In this experiment, actually, we're going to inject latencies between 0 to 10 milliseconds so that we can evaluate how's the performance of unified vMotion if we want to migrate both memory and disk state over metro distance. So now let's first take a look how our test configuration look like. In this experiment, we have two identical ESX hosts on source and destination side. And each ESX host is going to have two 10 gig NICs. And in some experiment, we only use one 10 gig NIC, and some experiment, we're going to use both. On the storage side, we have two eMMC SAN array attached to each host. For unified vMotion, we don't have any shared storage because we're going to transfer both memory and disk state over the network. For storage vMotion, for comparison purpose, we're going to actually attach the destination array to source host so that we can perform storage vMotion between the source and destination arrays within the same host. So let's take a look at the disk migration performance first. In this experiment, as I mentioned before, we have to run guest workload, which is disk I/O intensive, so that we can compare the disk migration performance between unified vMotion and storage vMotion. Here we run some DVD store workload, which is the open source OLTP workload, and we measure the guest performance in terms of number of orders per second. And we are interested in the migration time of the disk migration portion as well as the total migration time. Also, we are interested in how the guest performance during this migration. So let's take a look at the result we have for disk migration. As we can see here, we almost have identical performance for disk migration between storage vMotion and the unified vMotion. So this is because in this setup, we have disk is the bottleneck rather than network. So network is much faster because we run one 10 gig NIC, link between these two hosts. This is a typical scenario in most of our enterprise environments. You will have much bigger pipe between the network, vMotion network, than the actual disk I/O. So second observation here is that for this particular workload, we can see the disk migration time dominated the total migration time. So the memory migration time only takes 16 seconds. So now let's take a look at the guest penalty during the disk migration. For storage vMotion, before we start migration, as we can see, the guest has about 400 orders per second. After we start storage vMotion, as Gabe described before, we need to do a linear clone path, which is going to read all the disk blocks from the source array and write to destination array. So during that disk migration phase, we're going to have significant read IOs from source array, which is going to have impact on the guest workload. Because this guest workload is disk IO intensive. So then we can see here that throughput in the guest actually dropped to about 250 orders per second. So this lasts about 250 seconds. Then we start switch over. The switch over typically takes 1 second, and then the guest workload actually dipped to 0, and then recover from destination to the same throughput. Now, interestingly, let's take a look at the guest penalty for unified vMotion. As we can see here, we almost have the same guest penalty during the disk migration phase. This is because for unified vMotion, we have the same amount of read IO from the source array. Then we have, even though the disk IOs are going to be piped through the vMotion network, so it has the same amount of guest penalty as the storage vMotion. However, notice here that after the disk migration phase, we're going to start the memory migration. During that time, we already finished our clone path. So we only mirror the guest IO to destination, to both source and destination array. So in this case, as we can see here on the yellow side, we have almost no guest penalty to this workload. Then the same switch over happens, and the guest workload is going to run on the destination. So the key takeaway here for disk migration is that because the unified vMotion leverages the same architecture as storage vMotion, we have the same performance result as storage vMotion from disk migration part. Now let's take a look at the memory migration. That's also another interesting aspect. So to able to measure the memory migration performance, we run a different workload here, which is the TATP workload. In this workload, it's both CPU and memory intensive, but not I/O intensive. So the objective here is the same. We want to measure the migration time as well as the guest penalty during the migration. And also, we're going to adjust the client workload so that we can make the guest workload from idle to moderate, then to heavy, on heavy workload. Here, the result shows we almost have the same performance result for memory migration part between unified vMotion and traditional vMotion. Although the traditional vMotion is going to use the shared disk, but our unified vMotion is going to transmit all the disk state as well. As we can see here, if we have heavy workload in the guest, then the precopy may not converge. For example, here when we run 64 TATP clients, the guest workload is busy enough and the pages get dirtied quick enough so that the precopy phase cannot converge. In that case, our new feature introduced in ES654 called DRS going to kick in, and which is going to disrupt the guest enough so that we can finish the migration. So that's one option. Another option is if you have enough resource, for example, you can add an additional vMotion NIC, then we can take advantage of both bandwidth for these two vMotion NICs, and then we can converge the vMotion without introduce SDPS. So for example, here, if we hook up another vMotion NIC, we can see that the total migration time is going to be reduced by 30%, and we don't have to introduce, even kick in SDPS. So now let's take a look at the guest penalty during traditional vMotion and unified vMotion. As we can see here, we almost have no guest penalty during the memory migration. This is because the dirty page tracking is cheap enough, and we are not going to disturb the guest too much during the memory migration phase. And interestingly, let's take a look at the unified vMotion, though, because in this unified vMotion, we're going to have disk copy phase as well, in addition to the memory copy phase. In this particular guest workload, because the guest workload is not disk I/O intensive, even though the disk copy phase, we're going to have lots of read I/O to the source array, we still don't disturb the guest too much. And we can see here, the guest workload is constant during the disk migration phase as well as the memory migration phase. So the key takeaway for this experiment is that because unified vMotion leverages the same architecture and code path as traditional vMotion for memory copy side, we have almost identical performance result as well between unified vMotion and traditional vMotion. As we know, we introduced a mature vMotion feature for traditional vMotion, which allow you to migrate your VM live between mature distance. Unified vMotion take advantage of the same feature. So we have the same optimizations for latency. So in this experiment, actually, we're going to run our unified vMotion over mature distance with different latencies. We add a NetARM host between these two ESX hosts, so we can inject latencies from 0 millisecond to 10 millisecond. In this, we run this experiment in 3 different configurations. We have 0.5 millisecond latency and 5 millisecond latency. Finally, we run against the 10 millisecond latency. In all those 3 cases, we can see the total migration time is constant. This is because our mature vMotion feature is going to optimize the vMotion traffic over the long latency network. So in summary, the performance study we have done here in our VMware lab shows that the performance result between unified vMotion and storage vMotion is the same in terms of disk migration, and the performance of unified vMotion and the traditional vMotion is the same in terms of memory migration. And we'll also leverage all the nice features for traditional vMotion, including mature vMotion, SDPS. Now, after we talked about the performance session, let's discuss some best practice when you want to configure and run your unified vMotion in your environment. First, we have done some performance optimization on VMFS layer for one block size file system. So if you're still running your workload on VMFS3, we would recommend you to upgrade your file system to VMF5 with one block size. Second, as we see from previous results, Martinique is very useful for heavy workload during the migration. And if you have multiple NICs, we would recommend you to configure them if you want to migrate intensive workload during the migration. When you configure those, make sure you configure Martinique in the subnet. Third, if you want to migrate a VM which has a snapshot or link clone, then the read-only portion of the disk chain is going to be migrated using our management network rather than the vMotion network. This is because the vMotion network only intends to migrate hot traffic, which is your hot memory, your hot disk. So if you want to migrate snapshot VMs, make sure you have enough bandwidth for your management network. Lastly, even though unified vMotion don't need any shared storage, but we do have some optimization here. We can take advantage of the VAI offload on the array side if the source ESX host has access to both source and destination data store. In this case, you're going to have less traffic on your vMotion network, and it will also be faster if you have the VAI offload. Now, let me introduce our product manager, Jennifer, to discuss our vMotion roadmaps in the future.
So let's look again at the vMotion feature timeline. Gabe first discussed the current capabilities of vMotion, including traditional vMotion and storage vMotion, which many of you around the world use day in and day out. Gabe then went on to discuss vMotion in vSphere 5.1, which is vMotion without the requirement for shared storage. We're very excited to bring this feature to you because we feel a broad customer base will be able to leverage this functionality right away, including SMBs who don't have expensive shared storage systems on the back end, as well as enterprises who don't have a shared storage configuration across clusters. However, we're not done. Today, we'll take a peek into the future of vMotion, and we'll begin by breaking management boundaries with cross vCenter vMotion. We commonly hear from customers today who host multi-VC environments that they must manually move their VMs across VCs. They do so with varying levels of regularity, but virtually all do it. As you know, this VM downtime is costly, and the process of exporting, importing, reconfiguring the VM at the destination is both time-consuming and tedious. Cross vCenter vMotion will make this process much easier. VMs will be able to use infrastructure regardless of which VC manages that infrastructure. And IT admins will be able to load balance and perform disaster avoidance scenarios across VCs without incurring any VM downtime. And lastly, cross vCenter vMotion is a critical enabler of my personal favorite, long-distance vMotion. More about that shortly. So cross vCenter vMotion is the live migration of the compute, storage, and network across VC boundaries in a single operation. This breaks management boundaries because you'll be able to migrate your VM across vCenter, data center, across your vCenter, data center, and folder objects. Customers right now frequently don't have shared storage across their VCs. These customers will be able to utilize the new unified vMotion architecture which will migrate your memory state and your storage in a single operation. At this point, we're often asked, what about the network? The VM network migration capability will happen totally encapsulated within the vCenter vMotion operation itself. Let's look one level deeper into the VM network migration capability. When a VM migrates across a VC, the VM network must migrate as well. So if a VM is attached to a standard switch at the source, then the VM can move to either a different standard switch at the destination or a distributed switch. If the VM is configured with a distributed switch at the source, then the VM must move to a different distributed switch at the destination. All of the DV port information will be migrated with the VM. An additional network configuration requirement is that the VM client or the end user needs to have uninterrupted access to the VM workload. This can be accomplished by having L2 connectivity for the VM network between source and destination. So you can use either the same VLAN, use VMware's VXLAN technology introduced in 5.1, or use any other third-party L2 extension or overlay technology. So what happens to the VM after it has migrated across the VC? Each VM will have its own unique identifier associated with it throughout its lifecycle. This will allow clients who need to plug into the VC environment be able to easily identify and track the VMs as they move from VC to VC. Historical data, such as stats, alarms, and events, will be preserved across vCenter servers. So a user will be able to look at it UI and be able to see a unified history of the VM, a continuous history, including data from both the source and destination VCs. The VM will interoperate seamlessly with DRS and HA solutions. So when a VM is placed on an HA or DRS-enabled cluster, the VM will perform admission control, get placed on the cluster, and then operate with any per cluster enabled solution. There are a few requirements that have to take place in order for vCenter vMotion to work. In order to see the inventory from the destination VC from the source VC, both the source and destination VC must belong to the same SSO domain. As we discussed from a networking perspective, there must be layer 2 connectivity for the VM network between source and destination. And additionally, the networking services such as firewall rules and NAT translation policies need to be consistent at source and destination. So we've talked about cross vCenter vMotion. However, customers are now elevating their virtualized infrastructures into the cloud. The virtual data center, or VDC, is a critical construct within the vCloud infrastructure. VDCs contain workloads packaged as virtual appliances or vApps. vMotion will continue to break management boundaries by supporting cross VDC vMotion. So cross VDC vMotion is a live migration of vApps across VDC boundaries. Users will be able to use cross VDC vMotion to onboard VMs from the VC environment onto the vCloud environment. And once on the vCloud, vApps will be able to move from vCloud to vCloud. VDCs contain services, and vApps use these services in order to enforce user-defined policies and SLAs. So when the vApp crosses a VDC boundary, these policies will move with the vApp and get applied at the destination. So let's look at an example. There's a user in an organization who uses infrastructure resources at both New York and New Jersey in the vCloud environment. This user decides that he wants to move his workload from the New York VDC to the New Jersey VDC. When he moves the vApp, all of the services, or all of the policies that are associated with the vApp are gathered and migrated with the vApp and then applied at the destination. And in this way, all of his workloads act the same in the New Jersey VDC as in the source New York VDC. So we've talked about breaking management boundaries with cross vCenter and cross VDC vMotion. We will also be breaking distance boundaries with long distance vMotion. So long distance vMotion is the ability to live migrate a VM across WANs over geo-distances. Customers right now are standing up new data centers in remote geographic locales for various reasons, while other customers are consolidating their data centers because they've acquired companies or are streamlining their business processes. Live long distance vMotion will allow these customers to migrate their VMs from data center to data center. Additionally, users will be able to optimize their disaster avoidance scenarios. Tier 1 applications will be able to be migrated live to the secondary site. And this secondary site can be at a geo distance, putting the VMs further geographically away from the disaster site. And long-distance vMotion will also allow you to live migrate your VMs in the cloudburst scenarios. There's a bit of infrastructure that needs to be in place in order for long-distance vMotion to work. From the networking perspective, there needs to be a secure vMotion channel for the VM data to safely cross the WAN. And similar to the cross-VC case, there needs to be an L2 connection from the source and destination for the VM network. And to handle your IP addresses, there needs to be a global site load balancer and NAT servers. From a platform perspective, users will be using the building blocks that we've provided from unified vMotion and cross vCenter vMotion. And lastly, on the storage side, we'll be supporting the configuration of live migrating long distance a VM without shared storage or any other specific storage requirement, as well as leveraging replicated storage arrays on the back end where available. So let's take a look at how the networking piece fits together for long-distance vMotion. I have a user who wants to connect to the VMware.com workload. The DNS server returns the public IP1 address for this workload. And this public IP1 is routed to the NAT server at Site 1. This NAT server translates the public IP1 into a private IP address that stays with the VM. So while this client is accessing the VMware.com workload at Site 1, the IT admin decides that his infrastructure is getting overutilized in Site 1 and wants to long-distance vMotion his VM to a second site. He initiates a long-distance vMotion with a vCenter server, and the VM crosses the secure vMotion channel and gets placed on the second vCenter server at Site 2. After the vMotion completes, the global site load balancer is updated with a new location. So when this client now creates another request for the VMware.com workload, the public IP address 2 comes back to the client and gets routed to this Site 2, the NAT server on the second site. This NAT server translates the IP address 2 to the same private IP address that the VM had at the source. So all new client connections from the users go directly from the client to Site 2, while all old existing connections continue to flow through Site 1, but travel through the L2 tunnel to get to the workload at Site 2. So from the platform and storage perspectives, long-distance vMotion will support 3 different types of architectures. The first architecture is the migration of the VM without any requirement of storage on the back end. This is simply a unified vMotion, the migration of the memory state and the storage backend over geo distances. This allows the maximum flexibility for your environment because you'll be able to long-distance vMotion the VM from any VC to any VC. We'll also be leveraging replicated storage arrays on the back end. In this case, we will require that you upgrade your firmware on your storage array to support VMware virtual volumes. vVols is simply an API into the storage layer so that it will expose the storage on the granularity of VMDKs instead of LUNs. We will take advantage of this replicated VMDKs, and instead of migrating the entire storage of the VM on the back, we will only be migrating the change bits along with the memory state over the storage array. For the active-active storage array, again, we require that the storage firmware gets upgraded to support virtual volumes. From the VM's perspective, for an active-active storage array, the array appears as if it's shared storage. In this case, we will only be doing a traditional vMotion across the active-active replicated storage array over geodistance. So in the first configuration, without any storage array requirements, this allows maximum flexibility of moving from any data center and any VC to any VC, and the latter two optimize for total migration time by leveraging the replicated bits of your storage array backend. So we've talked about traditional vMotion, storage vMotion, vMotion vSphere 5.1, which is a vMotion without the requirement for any shared storage. And then we talked about features. vMotion breaking management boundaries with cross vCenter vMotion, cross VDC vMotion, and lastly, long distance vMotion. These are all building blocks to what we have as our complete vMotion solution. So that users will be able to move their VMs and vApps from private cloud to private cloud, and also from the hybrid cloud perspective of private to public and public to private cloud to distances all over the world. This is our vision for what we call vMotion Anywhere. So the key takeaways from this talk are that we are now delivering the new vMotion vSphere 5.1 capability, which is the vMotion without any requirement for shared storage. The architecture of this configuration is that we migrate the VM's memory state and storage in a single atomic operation. The performance of vMotion in vSphere 5.1 approximates that of traditional vMotion technologies. That is, the storage migration approximates that of storage vMotion, and the memory migration component approximates that of the traditional vMotion. And then we talked about the roadmap, in which we'll be crossing management boundaries with cross vCenter and cross VDC migrations and long distance vMotions. All of these building blocks provide the capability into what we're calling our vMotion Anywhere initiative. Thank you. So we'll take questions. Please go to the microphones if you have a question.
Do you support RDM LUNs in Unified vMotion? RDM LUNs.
Yeah, so for Unified vMotion, you have to have your LUN be accessible by both source and destination hosts. So in that case, we're going to only move the mapping file to the destination data store for Unified vMotion.
Yeah, unless you want to convert the RDM to a VMDK during migration, in which case then there doesn't have to be any common shared storage.
Okay. Okay, thank you.
Can you move from one RDM to another?
Sorry, could you repeat the question?
If you're doing the unified vMotion, can you move from one RDM to another RDM on the other side?
Today, we do not support RDMs as a destination for a storage vMotion or a unified vMotion. We can only move RDM pointer files. But yeah, we're happy to convert from RDM to VMDK.
So which vStorage technology is going to use the VXLAN exactly? The future one or the unified? So VXLAN. So which vMotion will be used using the VXLAN? So what I understood is that in 5.1, we'll have support for the VXLAN, right? And my question is that VXLAN will be used by which vMotion? Is it the futuristic, like long distance vMotion, or across the VDCs, or across the vCenters, or all of them?
So you can use VXLAN wherever you need, basically, to bridge your subnets. So whenever you need L2 connection, then you can use your VXLAN. So if you have separate L2s within your vCenter environment, then you can use your VXLAN.
So that could be even in 5.1, that you are doing the migration between two vCenters, which are on the different L2 connectivity. Right. Yeah. All right, thank you.
Just one quick question. On the network settings for our NIC cards using vMotion, in 4 and presently in 5, we're only allowed to set it to a full 1 gig. Are we allowed to switch over to auto sensing in 5.1, or do we have to stay on the manual fixing of 1 gig?
I didn't hear that. Did you hear that?
I only caught a little bits of that, sorry.
On your network card setting for a vMotion network card, when we set the setting on the card, we usually have to set it to full 1 gig on a manual setting. Normally, we set all of our other NICs for auto sensing. Can we switch to auto sensing in 5.1, or do we still have to stay on manual mode of 1 gig? No?
Again, I only caught bits of that. It's hard to hear back there, but it sounds like the question is about auto sensing speed, or?
Yeah. Presently on the network card.
Okay.
You set it to manual full gig. 5.1, and we switch it to auto sensing. We still have to keep it manual.
Interesting. So the question is whether or not you can switch to auto-sensing for the speed in ESX51 for the vMotion NICs. Typically, auto-sensing should work just fine, but it's possible there's something wrong with the interaction of ESX and your particular type of NIC that makes auto-sensing misreport the speed to VC, so it doesn't know what speed the NIC is. What were you seeing when you tried to use auto-sensing?
That's been the policy that's been set. I know before, we were all too sure. I know the boss told me keep set to that. I'm not switching to auto-sensing. And I thought it might have changed in 5.1.
So auto-sensing shouldn't be necessary unless for some reason the NIC isn't reporting the proper speed up to VC, in which case the number of concurrent vMotions you'll be able to issue in VC will be limited down to potentially even 2. But I would try disabling manual, switch back to auto-sensing. And so long as VC still lets you issue 4 concurrent vMotions, then everything's fine. Thanks.
2 questions. One on the VXLAN, is there any intention to add route injection capabilities so that you don't have to route through the origin site in the future?
Yeah, they're working on that now to have 2 different gateways and to work on the routing problem. So that's on their roadmap.
Great. And quick question on best practices for the vMotion network with network I/O control as a factor here. Would it be possible, or not? Would it be possible? Would it not be a good way to go to just set up your vMotion network as a dedicated VLAN and then spread it across all available NICs and use network I/O control to make sure that it doesn't overwhelm the other traffic?
That is also a valid approach. I mean, the whole idea behind the vMotion network is just to provide some sort of dedicated resource for vMotion that is also a secure network. So if you're still providing some reliability of bandwidth by way of either QoS or NIOC, then yeah, that should work just fine. But just keep in mind, it should also be over some sort of secure network. So,
thank you.
Storage vMotion, you are essentially doing 2 writes for every command now, and you have to wait both of them to finish before you can tell application. So what is the recovery mechanism? Let's say a destination storage is misbehaving and it's timing out or it's not responding. So now you are penalizing your normal I/O because the second one is not responding. So how do you deal with that?
Sure. So yes, on the mirror path, we do have to wait until the I/O finishes for both the source and destination data store. If one data store is slower than the other, then all I/O will run at the rate of the slower data store. If something goes wrong with the data store and eventually it times out or stops responding, we will eventually fail the I/O, report that. In some cases, that I/O failure might be reported to the guest. In general, we try to catch that and shield the guest from seeing any destination-side I/O errors. But in general, we hope that you're not doing a lot of storage vMotions to failing destination data stores.
Actually, we're going to have even a smooth transition if you migrate from a faster data store to a slow data store. So you're going to see like gradually the guest workload are going to adjust to the slow data store on this machine.
Depending on the I/O distribution, yeah.
I have one more question. So as you mentioned that the UUID of the VM across the vCenters are going to be unique now or same. So do we expect any changes in the format of the UUID?
Do we expect any change in the update?
So from the current format of the UUID of the VMs, should we be expecting any changes in the future to support the unique UUID across the vCenters?
Not really, because right now we have instance UUID in VM's config. So that instance UUID is going to be keep the same after we migrate between vCenters. But the managed object reference is going to change because that's not a unique UUID right now.
Okay, thank you.
Yes, this is in regards to the vMotion. Are you going to provide a way for admins to force the disconnect of remotely mounted CDs and VMware tools, et cetera, in an automatic mode? Because we have hundreds of VMs, and invariably I have 5 to 10 VMs that have CDs mounted, and we have to go in, force them off, move the VM manually, and power it back on, and it takes a long time for us to do that. So I haven't seen that feature, but it's something I'm hoping to see in 5.1, et cetera.
Okay.
Any thoughts?
Well, yeah, it's not our team, but the team has it on the roadmap.
I guess the request then is mostly just that if we can't vMotion the VM, for example, it has a local CD attached, you would want us to tell you that and then give you the option to power the VM off and move it cold, or?
Yeah. I mean, something that simple, or either break the connection and move it anyway.
Okay, potentially even detach the CD-ROM drive and move it.
But this is only for the...
I think it should already there.
This is
Yeah,
only
if
for
you
the-
disconnected the CD-ROM, we should be able to allow you to do the migration, but we're going to give you a warning.
Yeah.
If you have, we should already have that.
So it sounds like this should be something that's automated, though.
Yeah, it's automated.
This is the
I have to do it
evacuation
like
mode,
10 or
right? And
20
that's the other
times
team
every
that's
time we
actually gonna be
evacuate a
supporting
host.
Okay, sure. I'm not sure if you have used the vSphere API, you can actually write a script to that. But, something like you want some batched mode to ignore all the warnings in the UI.
Yeah.
Okay.
Okay.
Regarding the unified vMotion, how much latency did you begin to see problems? You tested at 10 milliseconds. When did you start seeing issues?
We've tested well beyond 10. In practice, we run automated testing up to 20, 40 millisecond latency. Performance, vMotion doesn't break with higher latencies. It's just performance degrades. It degrades to the point that it becomes unacceptable from our perspective, and it's no longer really a vMotion, because a core property of vMotion is that the VM should not experience any loss of connectivity or the like during switchover from source to destination. As latency increases, that becomes less true. So we try to keep people in the 10 millisecond range because we can still maintain those same guarantees we provide. Beyond 10, it will function. It's just performance will degrade. I definitely would not recommend anything beyond 20, and really 10 is the safe margin.
Thank you.
Thanks. What latencies have we tested? As I said, we regularly test up to 40. We've done some testing as high as 100 or so, but definitely you do see severe performance degradation there. We are definitely, in the future with long-distance vMotion, we're actively working to fix that, so beyond 10 will scale seamlessly. Yep.
So are you guys working on something to fix the layers of right, so if I've got a layer 2 router stretched across multiple places, where my routing still has to come from the original site, but it's going to go across that layer 2 or wherever it is supposed to fly.
Yeah, that's...
So then we have site 1 IP ranges, site 2 IP ranges.
Yep.
If we could change an IP so we're down routing to site 2,
Mm-hmm.
do something with my DSS to fix it. Are you guys working on that?
We're doing some research on that area, but another question I have to you guys is, do you have any configuration to take advantage of Lisp, like Cisco provides or something? Because the problem is really once you want to keep L3 network connectivity between two sites, then you have to have your service provider or your agent network to provide some Lisp capabilities.
So bigger organizations like mine, we've got a huge backend network where we've got all of our customer sites to the backside.
Okay.
For us, it's important that we have.
And you don't need any public access from outside of your range? Okay, so those probably we can, research more on this front.
Yeah. Yeah, you're exactly the case we're really interested in. I mean, that's the problem we're trying to tackle. So.
Okay.
So you mentioned about having a layer 2 connectivity with the L solution. Keeping the same VLAN and IP subnet costs the particular issue that I've run into is that if a link goes down, the gateway gets primary site is always active, the secondary is standby. So when the link goes down, the secondary will become active again. So since it can't see the circuit, that would provide the gateway to do that. So one thing that I have a question about is that as soon as you start using the secondary data center, all the activity actually changes. You mentioned something about the global cycle bounds. Is that the root product, or is that something? For example, right now we have F5.
Exactly.
And the overnight is update DNS.
That's the idea.
That's simply. Is that the what triggers the update? You said something about the vSphere or overnight update with F5.
Yep.
So it's intended to work with your existing infrastructure, whatever you have infrastructure. So the idea is not to make it by mistake.
Yeah, because that eliminates the IP and the
Yes. So unified vMotion is out now. Long distance is
In the future.
Yeah, but that layer 2 could be virtual layer 2, right? So we have lots of solutions there right now. You know, it don't have to be your actually physical LAN over to network.